with reference to the manufacture of carbon fibre components. A. Describe each of the following processes and its advantages. 1. Vacuum bagging. 2. Autoclave curing. 3. Resin transfer moulding. B. List the type of component that each process described in Part A is best suited to. Here is a breakdown of each process. Vacuum bagging. The process: a dry fibre preform is placed in a mould and then covered with a vacuum bag. The air is evacuated from the bag, which applies pressure to the preform and forces the resin to flow through it. The part is then cured under heat. Advantages: simple and relatively inexpensive process. Can be used with a wide variety of mould materials and shapes. Good for producing parts with a high fibre volume fraction. Disadvantages: limited to parts with simple geometries. Voiding, which is air pockets, can be an issue, and not suitable for high performance applications. Autoclave curing process. The vacuum bagged part is placed in an autoclave, which is a pressure vessel that can be heated and pressurized. The pressure helps to consolidate the laminate and eliminate voids. Advantages: produces high quality parts with excellent surface finish and low void content. Suitable for complex geometries and high performance applications. Disadvantages: expensive process due to the high cost of autoclaves. Limited throughput due to the long cycle times. Not suitable for large parts. Resin transfer moulding (RTM) process. The dry fibre preform is placed in a closed mould and then resin is injected into the mould under pressure. The part is then cured under heat. Advantages: can produce high quality parts with good surface finish and low void content. Faster cycle times than autoclave curing. Can be used for larger parts than vacuum bagging. Disadvantages: it's a more complex process than vacuum bagging, requires specialized molds and equipment, and not suitable for all geometries. With reference to the heat treatment of steel. A. Explain which steels this process is best suited to. B. Explain each of the following processes, making reference to mechanical properties and internal structure. 1. Hardening. 2. Tempering. Heat treatment of steel. Specific processes. Steels best suited for heat treatment. Heat treatment is particularly beneficial for specific types of steel, primarily those with medium to high carbon content, 0.2 to 1%. These steels experience significant changes in their mechanical properties due to the heat-driven transformations in their internal structure. Some examples include: A. Hypoeutectoid steels, carbon content less than 0.77. These steels can achieve significant hardening through quenching, forming martensite with high strength and hardness. 2. Eutectoid steel, 0.77% carbon. This steel regularly and readily transforms into perlite, a mixture of ferrite and cementite, during slow cooling, achieving a good balance of strength and ductility. Hypoeutectoid steel, with a carbon content of greater than 0.77%, can achieve high wear resistance due to the presence of cementite, which is iron carbide. However, their weldability and ductability are very limited. Steels with a very low carbon content, less than 0.2%, and high alloy stainless steels generally benefit less from heat treatment due to their inherent properties or limited transformation potential. B. Heat treatment processes explained. 1. Hardening. The process. Steel is heated above its critical temperature, around 723 degrees Celsius, austenitizing its microstructure, transforming it into austenite, a high carbon phase. This is followed by rapid quenching, usually in water or oil, which traps the high carbon austenite structure as a metastable phase called martensite. Mechanical properties. properties. Hardening significantly increases the strength and hardness of the steel, but at the expense of ductility and toughness. Martensite is very strong and hard, but also brittle and prone to cracking. Internal structure. The rapid quenching prevents carbon atoms from diffusing and forming equilibrium phases like pearlite. Instead, austenite transforms into martensite, a distorted tetragonal lattice structure with a high carbon content, leading to high strength and hardness. 2. Tempering the process. Hardened steel is reheated to a lower temperature, typically between 150 degrees centigrade and 500, and then cooled slowly. This allows some of the martensite to transform back into less brittle phases like ferrite and cementite, depending on the tempering temperature. Mechanical properties. Tempering reduces the hardness and strength of the steel compared to the hardened state, but significantly improves its ductility and toughness. This makes the steel more resistant to cracking and failure under stress. Internal structure. Tempering allows carbon atoms to diffuse and form more stable phases like ferrite and cementite. The specific phases formed and the degree of transformation depend on the tempering temperature, influencing the final balance of strength, ductility, and toughness. Therefore, hardening and tempering are complementary processes. Hardening provides high strength and hardness, while tempering improves ductility and toughness, allowing for a tailored balance of properties for specific applications. With reference to stresses within engineering materials. A. Explain each of the following terms. 1. Tensile stress. 2. Shear stress. 3. Compressive stress. B. List 2 components within a diesel engine that are subject to the effects of each of the 3 stresses listed in Part A. C. State the component in a 4-stroke diesel engine that has a maximum recommended service life due to constant cyclic stress. A. Explaining different types of stresses. 1. Tensile stress. Definition: a pulling force that acts to elongate a material, stretching it in the direction of the force. Imagine pulling a rope to extend it. Shear stress. Definition: a force that tends to slide or deform one part of a material relative to another along a parallel plane. Imagine sliding 2 bricks against each other, causing them to deform and potentially be damaged. Compressive stress. Definition: a pushing force that squeezes or compresses a material, shortening its length in the direction of the force. Imagine stacking heavy weights on top of a block, pushing it downwards and potentially crushing it. B. Components experiencing different stresses in a diesel engine. Tensile stress. The connecting rod. The pull of the piston on the connecting rod creates tensile strength throughout its lengths. Cylinder head bolts. The pressure generated during combustion pushes outwards on the cylinder head, requiring the bolts to resist this tensile force. Shear stress. Crankshaft bearings. The connecting rod rotates on the crankshaft bearing, creating frictional shear stress between the 2 surfaces. Gear teeth. When gears mesh, their teeth slide against each other, generating shear stress at the contact points. Compressive stress. Piston. The combustion pressure pushes down on the piston, creating compressive stress throughout its crown. Cylinder walls. The pressure inside the cylinder also pushes outward on the cylinder walls, subjecting them to compressive stress. C. The component with the maximum cyclic stress in a 4-stroke diesel engine The component in a 4-stroke diesel engine with a maximum recommended service life due to constant cyclic stress is the piston and its rings. These components experience repeated cycles of high pressure during combustion, followed by release of pressure during exhaust and intake strokes. This constant cycling, along with high temperatures and friction, contributes to wear and tear, necessitating a recommended service life for their replacement. Explain each of the following engineering terms, stating one material that exhibits each property. A. Brittleness. B. Ductility. C. Hardness. D. Malleability. E. Toughness. Here are some definitions of the terms and an example of a material that exhibits each property. Brittleness. A material that is brittle will break or crack easily under stress. An example of a brittle material is glass. Ductility. A ductile material can be drawn into thin wires. An example of a ductile material is copper. Hardness. A hard material is resistant to scratching or indentation. An example of a hard material is diamond. Malleability. A malleable product can be hammered or pressed into thin sheets. An example of a malleable material is gold. Toughness. A tough material is resistant to breaking under impact. An example of a tough material is rubber. With reference to gas metal arc welding, MIG, of mild steel. A. Describe the process. B. Explain, with reasons, the surface preparation required. C. List 3 advantages and 1 limitation. A. The MIG welding process. MIG welding, also known as metal inert gas welding, is a semi-automatic welding process that joins metals using a continuously fed consumable solid wire electrode and an inert shielding gas. Here's a breakdown of the steps. 1. Preparation. Clean the weld area thoroughly to remove dirt, grease, rust, paint, and any other contaminants that can weaken the weld and introduce impurities. 2. Setup. Choose the appropriate wire and inert gas, e.g. argon or argon CO2 mix, based on the material and desired weld characteristics. Install the wire and gas cylinder. Set the wire feed speed and welding current according to the material thickness. 3. Welding. Hold the welding torch at the appropriate angle and distance from the joint. As you trigger the welding run, the wire feeds continuously and an arc forms between the wire tip and the metal, melting both materials. The shielding gas protects the molten metal from atmospheric contamination. 4. Travel speed. Move the torch steadily along the joint seam at a controlled speed, melting and joining the metal while leaving a continuous weld bead. 5. Cleaning. Allow the weld to cool completely and then remove any slag residue with a chipping hammer or wire brush. B. Surface preparation and its importance. Proper surface preparation is crucial for achieving strong and high quality MIG welds in mild steel for several reasons. Contaminants. Dirt, grease, rust and paint can all prevent the molten metal from properly bonding with the base metal, leading to weak welds and potential porosity, gas bubbles, within the weld. Oxidation. Rust and oxidation layers create impurities that can affect the weld strength and introduce slag inclusions. Smooth melting. Clean and prepared surfaces offer a better contact surface for the molten metal, allowing for smoother melting and a more consistent weld bead profile. Therefore, thorough cleaning with grinding, wire brushing, or other appropriate methods ensures optimal weld quality and performance. C. Advantages and limitations of MIG welding. Advantages. 1. Versatility. Handles a wide range of materials and thicknesses with ease. 2. High deposition rate. Creates thick and strong welds quickly due to the continuous wire feed. 3. Cleanliness. Inert gas shielding minimizes spatter and fumes compared to other welding processes. Limitation. 1. Wind sensitivity. The shielding gas can be easily affected by wind, requiring shielding devices in outdoor environments for consistent weld quality. MIG welding offers a balance of ease, speed, and quality for mild steel welding, making it a popular choice for various applications. However, its wind sensitivity needs to be considered for outdoor work. Explain each of the following terms. A. Galvanic corrosion. B. Cavitation damage. C. Erosion damage. D. Stress corrosion. E. Atmospheric corrosion. A. Galvanic corrosion. Imagine a scenario where two dissimilar metals touch and are immersed in a conductive solution, the electrolyte, like seawater. This seemingly innocent contact can trigger a treacherous process called galvanic corrosion, and here's what happens. 1. Dissimilar potentials. Each metal has its own electrical potential, like a battery, but at different levels. The more active metal, with lower potential, acts as the anode, while the less active one, with higher potential, becomes the cathode. 2. Electron flow. Driven by the potential difference, electrons flow from the anode, active metal, through the electrolyte to the cathode, less active metal. 3. Metal dissolves. At the anode, metal atoms lose electrons and dissolve into the electrolyte as ions. This is where corrosion occurs, eating away at the anode metal. 4. Cathodic reaction. Electrons reaching the cathode react with the electrolyte, usually oxygen and water, to form harmless compounds like hydroxide ions. This cycle continues, relentlessly corroding the anode while protecting the cathode. The severity depends on factors like the potential difference between the metals and the conductivity of the electrolyte. Avoiding direct contact between dissimilar metals, using sacrificial anodes made of even more active metals, or supplying protective coatings are some ways to combat galvanic corrosion. B. Cavitation damage. Picture a fast-flowing fluid swirling around an object, creating bubbles due to pressure drops. When these bubbles collapse violently near a solid surface, the impact sends miniature shock waves like microscopic explosions. This phenomenon is called cavitation, and its destructive force can cause significant damage, aptly named cavitational damage. The shock waves erode the surface, creating pits, grooves, and rough patches. This type of damage is particularly common in propellers, turbine blades, and other components exposed to high-speed liquids. Materials with better tensile strength and resistance to fatigue are preferred to combat cavitation. Additionally, optimizing fluid flow and reducing pressure fluctuations can help mitigate the problem. C. Erosion damage. Erosion, in the context of materials, describes the gradual removal of surface material by the abrasive action of fluid or solid particles. Imagine sandblasting against a metal surface. That's essentially erosion damage. It can manifest as scratches, grooves, or even complete wear-through in severe cases. Pipelines, pumps, valves, and other components exposed to fluid flow with solid particles like slurries or sand-laden water are particularly susceptible to erosion damage. Choosing abrasion-resistant materials, modifying designs to reduce flow velocity and particle impact, and implementing protective coatings are crucial to prevent this type of wear and tear. D. Stress corrosion. Imagine a metal under constant stress, like a bridge bearing the weight of vehicles. This stress, combined with a specific corrosive environment, can lead to a type of localized attack called stress corrosion. It's like a double whammy, where the stress weakens the metal and the corrosive environment exploits these weaknesses, leading to cracks and fractures. Certain materials are more susceptible to stress corrosion in specific environments. For example, stainless steel under chloride stress in seawater is a classic example, identifying potential stress factors and corrosive environments, choosing resistant materials and employing stress-relieving techniques are essential to manage this type of damage. E. Atmospheric corrosion. This is the most common type of corrosion, the one we see daily on everyday objects exposed to the elements. Rain, wind, sunlight, and pollutants in the air combine to form a constantly fluctuating corrosive environment. The process usually involves oxidation, where metal atoms react with oxygen in the air, forming oxides like rust on iron or patina on copper. Atmospheric corrosion rates vary depending on the metal, the specific environment. For example, coastal areas tend to be more corrosive, and protective measures like coating or surface treatments. Regularly cleaning and maintaining surfaces, choosing corrosion-resistant materials, and applying protective coatings are effective strategies to minimize atmospheric corrosion. List 5 different methods of remotely monitoring the content level of a fuel oil service tank, explaining their operating principle. Here are 5 different methods for remotely monitoring the content level of a fuel oil service tank. 1. Float switch system. Principle: a mechanical float attached to a lever rises and falls with the fuel level in the tank. As the level changes, the level triggers switches at preset levels, sending electrical signals to a remote indicator or control system. Advantages: simple and reliable, cost-effective, suitable for basic level monitoring. Disadvantages: limited to discrete level readings, prone to mechanical wear and tear, and may not be suitable for high-precision applications. 2. Hydrostatic pressure transmitter. Principle: a pressure sensor is installed at the bottom of the tank. The pressure exerted by the fuel column on the sensor changes with the liquid level. This pressure is converted to an electrical signal and transmitted to a remote indicator or control system. Advantages: continuous and accurate level monitoring can be calibrated for high precision, suitable for deep tanks. Disadvantages: requires installation at the bottom of the tank, can be affected by temperature changes in the fuel. 3. Capacitance probe sensor. Principle: a probe with electrodes is inserted into the tank. The dielectric constant of the space between the electrodes changes as the liquid level rises or falls, affecting the overall capacitance. This change is measured and converted into a level reading. Advantages: contactless measurement, suitable for various liquids, continuous and accurate level monitoring. Disadvantages: sensitive to changes in the liquid properties like conductivity and contaminants, requires careful calibration. 4. Ultrasonic sensor. Principle: an ultrasonic sensor emits sound waves and measures the time it takes for the reflected waves to return from the fuel surface. The time difference correlates to the distance to the liquid level, allowing for level calculation. Advantages: non-invasive, suitable for various tank shapes, and can be used in harsh environments. Disadvantages: requires clear line of sight to the liquid surface. It may be affected by tank geometry and turbulence. 5. Guided radar level transmitter. Principle: a metal probe with radar pulses travels up and down the inside of the tank. The reflected pulses from the liquid surface provide information on the distance to the fuel level. Advantages: highly accurate and reliable, suitable for tall or irregularly shaped tanks, unaffected by tank conditions. Disadvantages: more expensive than other methods, requires installation of the guiding structure inside the tank. Explain, with the aid of a sketch, how the fluid level in a tank can be measured using ultrasound energy. B. State 2 advantages of using ultrasound. C. State 2 limitations of this type of measuring device. A. Ultrasonic level measurement with a sketch. Imagine a sensor mounted above or inside a tank, sending out high-frequency sound waves, ultrasound, towards the fluid surface. Here's how it works. Let's look at the sketch. Transducer. The sensor acts as both a transmitter and receiver of ultrasonic waves. Pulse emission. The transducer emits a short burst of ultrasonic energy towards the liquid surface. Echo reflection. The sound waves are reflected back from the liquid surface, similar to how your voice echoes against a wall. Time measurement. The transducer measures the time it takes for the reflected pulse to return. Distance calculation. Knowing the speed of sound in the air or tank material, the travel time is converted to the distance d traveled by the waves. Level calculation. Since the distance d represents twice the actual distance to the liquid surface, h dividing d by 2 gives the desired fluid level. Key points. The method relies on the precise measurement of the time it takes for the sound waves to travel and return. The speed of sound is a crucial factor and might need adjustment based on temperature or tank material. B. Advantages of ultrasonic sensors. Non-invasive. No contact with the liquid is required, eliminating risks of contamination or interference. Versatility. Works with various liquids and tank shapes. offering flexibility in application. C. Limitations of ultrasonic sensors. Line of sight requires a clear path between the sensor and the liquid surface. Obstacles or tank geometry can affect accuracy. Sensitivity to conditions. Foam, turbulence, or temperature changes in the liquid can impact the reflected sound signal and affect readings. Remember, ultrasonic level measurement offers a powerful tool for non-invasive and versatile level monitoring. However, understanding its limitations and ensuring suitable conditions for accurate operation is crucial for effective liquid level management. With reference to hydraulic governors fitted to alternators designed to run in parallel. A. Explain why these governors have adjustable integral action. B. Explain, with the aid of a load frequency diagram, how two generators operating in parallel are able to achieve a stable load share with a 50-50 ratio. A. Adjustable integral action. Hydraulic governors in parallel alternators have adjustable integral action for two main reasons. 1. Eliminating steady-state speed errors. In a system with multiple generators sharing a load, slight differences in governor characteristics or mechanical imperfections can lead to steady-state speed errors between generators. Integral action in the governor accumulates the error signal over time, gradually adjusting the fuel supply until the speed error is eliminated. This ensures all generators maintain the same speed, synchronism, regardless of minor variations, promoting stable parallel operation and load sharing. 2. Achieving desired droop characteristics. In parallel operation, governors are configured with a specific droop characteristic. This refers to the decrease in generator speed with increasing load. Adjustable integral action allows fine tuning of the droop, which determines how much each generator contributes to the total load change. By adjusting the integral gain, engineers can achieve the desired load sharing ratio between generators, such as a 50-50 split. B. Load frequency diagram and 50-50 load sharing. A load frequency diagram helps visualize the behavior of generators in parallel operation. Here's how two generators achieve a 50-50 load share. 1. Initial conditions. Let's assume both generators share the total load equally, 50% each, and operate at the nominal frequency F0. This point is represented by the intersection of the individual generator droop curves, G1 and G2, with the total load line, P tot. 2. Load change. When the total load increases, P tot increases, both generators experience a slight decrease in speed due to their inherent droop characteristics. The speed drop is larger for the generator with a steeper droop curve, greater integral gain. 3. Integral action and load sharing. The integral action in each governor integrates the speed error over time. In response, the governor with the larger speed drop adjusts its fuel supply more significantly, causing its frequency to recover faster and take on a larger share of the increased load. The other generator's frequency recovers slowly, resulting in a smaller load increase. 4. Equilibrium. This process continues until a new equilibrium is reached where the speed difference between generators is minimal and they share the increased load according to their droop characteristics. With properly adjusted integral gains, both generators can achieve a 50-50 load share at the new operating point. Here's the diagram. We're looking at two downward sloping curves, G1 and G2, representing the droop characteristics of generators. A horizontal line, P tot, represents the total load. The intersection of these lines represents the operating points at different load levels. When the load increases, both curves shift down, but the one with the higher integral gain shifts more, leading to a new equilibrium point where the load is shared equally.